So this is the last part in section 8.2. We'll talk about the actual electrons that are transferred in ionic bonding. And the electrons that are transferred are always the valence electrons. And the valence electrons, remember, are the s and p electrons in the highest energy level. And so, for example, in sulfur, sulfur would be 1s2, 2s2, 2p6, 3s2, 3p, 1, 2, 3, 4. So it would have 4 plus 2 or 6 valence electrons, just like group 16 would show. So 1, 2, 3, 4, 5, 6. And then potassium, of course, would just be 4s1, and so it would have 1 dot on it. And to obtain an octet, this potassium would give 1 electron away, this potassium would give 1 electron away, and then we'd have sulfur with 2 more electrons would look like argon, and then we'd have potassium right here with 1 less electron each, and now they would have the noble gas configuration of argon. So it's the s and the p electrons that participate in bonding. The confusion lots of times comes in, but what about transition metals? So transition metals are these guys right in here. They're metals, and they frequently form with nonmetals. They include these guys down here. Frequently form with nonmetals to make ionically bonded substances. So let's just take a look at transition metal ions. So because ionization energies increase rapidly for each successive electron removed, the lattice energies of ionic compounds are generally large enough to compensate for the loss of up to only 3 electrons from atoms. Thus we find cations with charges of +1, +2, or +3 on ionic compounds. Just like these guys, +1, these guys +2, these guys generally +3. Most transition metals, however, have more than 3 electrons beyond a noble gas core. Silver, for example, has krypton and then 4d10, 5s1 electron configuration. Metals of group 1b, like copper, silver, and gold, often form +1 ions. They'll lose that 5s1 electron right there, and then there'll be copper 1 something, silver 1, silver is almost always +1, and gold 1. Now, in forming silver +1, the 5s1 electron is lost, leaving a completely filled 4d subshell of electrons. As in this example, transition metals generally do not form ions that have a noble gas configuration. They'll just have a filled d sublevel, not necessarily the octet rule. And so we can see that the octet rule, although useful, is clearly limited in scope. Recall from section 7.4, that was one where we looked at electron ionization energy, and then we also looked at electron affinity. That when a positive ion forms from an atom, electrons are always first lost from the subshell having the greatest value of n. In other words, they're from like the 2s, this is the n number, 3s, this is the n number right here. So these would be the electrons lost if it was 2s2, 3s1. Well, these would be the electrons that would be lost first. Thus, in forming ions, transition metals lose the valence shell s electrons first, then as many d electrons is required to reach the charge of the ion. For instance, in forming Fe+2, the Fe, which has the electron configuration 3d6, 4s2, the 4s2 electrons are lost first, and then it would bite into the 3d10s to give it like a +3 charge or some further charge. So it loses s's first, then it loses d's as needed to become whatever charge it is. So the general rule that we talked about, the octet rule, we found out there's a little weakness. And we found out that things don't always form 8 electrons, especially if they're in this special area called the transition metals right here. These guys pretty much hold to that rule. These guys hold to that rule. These guys, well, every once in a while, D's as needed. Good luck with your ionic bonding.